So previous class we covered a complicated pendulum. We started with a simple pendulum, right? But let's talk about the pendulum again. So what we know about the pendulum is the following. So I'm going to call this one X, this one Y. And there's this length right here. There's an angle theta right here. This is the length L. And then there's a little bar right here with mass M. All right, so if this was physics 1, you would describe this with the two coordinates X and Y. Then you probably would solve for a free body diagram. And you would say, here's this guy. There's a force acting in this direction. What is this force?
Gravitation. Gravitation.
Mg?
Yeah.
Okay. And then there's another force, right? And you guys have done this, this tension, solving for this tension, and then solve for the Newtonian method tells you that this guy is given to you by the tension X component divided by L. And this other one has to be for ME minus that tension divided by L. Now, with that in it, you can solve for the system. You have a constraint. There's a constraint here. And that is this L squared is equal to X squared by Y squared. Right? Okay. And then you pose a constraint and you can solve for the equations of motion. And you get the first one is this one. And then from that, you can solve for the tension. And this tension is so this is a straightforward problem. You wouldn't be afraid to tackle it in physics 1, right? It's kind of complicated, but not too much. Good for physics 1.
And this will be NGL of theta.
Sorry? So this is the tension, right? And it's directed in that direction. All right. So you wouldn't be doing this problem though if you had more complicated constraints. Yeah.
Is the unit of this T, is it force?
Force, yeah.
So why are we dividing T by L in this ODs, like minus Tx by L?
So that's how I solved it in physics one. That's my tension.
I think I'm confused with which one is tension and which one is actually kinetic energy.
Yeah, so that's just the length plus the tension. Yeah, let me get back to you. I'm not sure. I mean, this is just a physics one example, right? Okay. But that's the solution for it.
So, but here it is tension, right? Tension equal to ml theta dot squared. Then we might have to multiply L with mg cos theta, right? To make the time.
Yeah. I think that's the case.
I don't think there should be the L.
You don't think the L goes there?
Yeah.
Yeah, I think that's my typo. I don't think the L goes there. Sorry. Yeah, because it's just dividing into the two forces, right?
Yeah.
Yeah, you're right. Okay, so yeah, take this out. But we do have a constraint, and it's a simple constraint, so you can do the physics one. Now, if you wanted to do a more complicated constraint, this method would crumble, so it would be hard. Like if you had a spring, right? Or if this length changed for some other reason, if it was changing with time. Whatever it was, it would be complicated. The other thing is when you did it with physics one, most of the work was done in figuring out what the tension is. Maybe you don't care what the tension is. Maybe what you're looking at is something where the tension is important, right? Then you will have to solve for this tension. I can think of a place where you might, type of calculation you might need tension for. How fast can I go with this, right? So this is telling us how fast it's going before the string breaks. So let's say I have a string that breaks after 100 newtons is applied to it. Then I would use that to figure out how fast can it go before it breaks. But most of the time, we don't care about those things. We just care about the motion, and what we're solving is this equation of motion. So in gradual mechanics, we don't waste time solving for the tension. All right, so let's look at this topic closely. I'll talk about it a little bit, only what I call a nomic constraint. And what this is, it's just a relationship. It's the relationships between coordinates. If we can write the relationship in a math way, then they're polynomial. So for instance, let's say we have this 0, where alpha can be 1 all the way to 3n minus n. So one thing to notice is that these constraints can be time dependent. They don't have to be, but they can be time dependent. I'm leaving this there because the math doesn't stop here if they're time dependent. And they're solved in terms of this generalized coordinates. And in this case, we have that n are the generalized coordinates that you're solving for. So there's a few of them that are part of the constraints. Those would be the ones that we have. So you have an equation for the constraint, and there's n equations, little n, that are part of the constraint, and you have q I associated with each of those. Okay? So that shows the math behind it. And what we have is that for our system, maybe the system is described by the following, where A, x of A depends on 1 all the way to n constraints. So this system will have n degrees of freedom. If we look at the simple pendulum, right? Theta is this degree of freedom. That's the only degree of freedom that matters for the simple pendulum. So that's the n degrees of freedom equals 1 for the pendulum. Q is equal to just theta. And that's how you describe the system, right? Your system is described just by theta. You don't need anything else to describe it in a simple pendulum. Okay. Questions? All right. So then let me bring up another topic related to this. I actually really like this topic because I use it in my research. So it's nice when you see something from classical mechanics, right, in your research. And these are the Lagrange multipliers. Is everybody familiar with Lagrange multipliers? No? All right. You might have seen it already. So the question is, we have constraints, polynomial constraints. How do we deal with those in the Lagrangian formulation? So the Lagrange multipliers is the way to solve the Lagrangian with constraints. So we have to come up with a new Lagrangian value. And this new Lagrangian is defined by we had our previous one. And now we're going to have this one. So this guy is a new variable. And this is the Lagrange multiplier. Okay. does this new Lagrangian depend on this variable? Yes or no? Yes. Does it depend on the time derivative of this variable? No. Come on, guys. Right? So, this Lagrangian does not depend on, yeah. So this Lagrangian does not depend, the new Lagrangian does not depend on the time derivative of this Lagrange multiplier. So what we have is that Lagrange equations we have to solve are for this lambda are equal to 0. So now you see, this is very similar to how you would solve for any coordinate. But this is a special coordinate that doesn't have a time dependence, so this automatically gives us 0. And you look right here, I'm just taking the derivative with respect to lambda, and there's no lambda over here, so therefore it's just this portion right here. Okay. So if I were to solve for this Lagrange equation, what do I get? Just a constraint. So I actually have something in this system, right? I already know what this Lagrange equation is for this x, and it's just the constraints that I have written down. So,
yeah, one quick question. You give lambda subscript alpha. That implying that you have multiple Lagrangian multipliers. Okay.
So you can have as many as you want, right? Have this many degrees of freedom. So you could have that only one of them is not going to be affected by a constraint. You could solve it like that. That would be the approach. So Lagrange equation for this x of the system, they are just as before. We have the time derivative of this guy. All right, now my tails are not fancy. Sorry about that. Didn't realize. They're the same. All right. So now we have the last Lagrange equation for what goes for the whole system, right? And this part, you already have seen the left-hand side, right? This left-hand side is the equation of motion for the system without the constraint. And then the right-hand side gives you that back the constraint forces. So equation of motion, constraint forces. And then you can solve this equation just as before. Okay. Questions? No? All right. So for instance, if you went back to the pendulum, you could write down the constraint with a new Lagrangian, right? And then you could figure out what the forces are and solve for the forces acting on the x direction, the y direction. All right. So,
I do have another question.
sorry, yeah.
You said that lambda was not time dependent. Is there a case where it could be?
I think I said lambda was not time dependent, just that the Lagrangian doesn't depend on this time derivative.
Is there a case where that will depend on the time derivative?
Not for the Lagrangian,
Okay.
not the way that we're doing it. But yeah, you can have a constraint that depends on time.
Okay.
All right, so let's look at it again with a pendulum. So we can parameterize, back to the pendulum, right? We can parameterize the constraint in terms of the coordinate data. So from the constraint that we have, that it's a system of length L, we have that x is given by L sine theta, and y is equal to L cosine. So now,
Isn't it minus 8 plus 3?
I think that the way I set up the system with this,
Why is this?
that's why it shows down. Just to not deal with the minus. So the particle moving in the plane, xy plane under the effect of gravity, will give you a Lagrangian. Potential. And then we have this can be reverted. And it's the 1/2 m L squared with theta dot squared. So what we did when writing this Lagrangian is that we actually put the constraint in already right here. So this new Lagrangian that we wrote is the one with already the constraint in it. If we want to do if we had to figure out how to do the tension for the Lagrangian column, then we have to go to the Lagrange multiplier method. So this is what we did before, right? And then we have to do this guy. All of that to calculate what is the equation of motion, right? So that's the approach that we did in the previous class. So now let me do it with the Lagrange multiplier method. This is the pendulum again. So from now on, all of the examples is just a simple pendulum. All right. so we have to write with, this is the same thing, particle moving in the plane. We're gonna add the Lagrange multiplier here for the constraint. And what we have to do is the following. This is my new Lagrange. In this case, I have same as before. This is the plane that is moving on. This is the same as before, energy y. And then now I need to add my multiplier. And then I have x squared plus y squared minus 12 squared. Questions? So here's the constraint, right? The constraint. So this is the go back over here. What do I want to do? So I have a relationship between the coordinates. And my coordinates are here, and that's my function of the constraint. So for the pendulum, I know that my constraint is that x squared plus y squared is equal to 12 squared. And that's the function that I need to do. Then I just multiply it by lambda.
And
I think that the half is just so the things work out nicely.
okay.
Yeah. So I'm putting the half. So this is my constraint, right? X squared plus y squared minus L squared is equal to 0. So now what I could do is figure out with this new Lagrangian what is equations of motions, not for theta, but actually for x and y. So calculate equations of motion for x and y. And this is where you solve for this guys, right? This one and this one. So I would have to take the derivatives, and then I have what I want. And if I solve for those guys, I get this is equal to lambda x, and this is equal to mg lambda. If I were to do the equation of motion for my third coordinate, which is this guy, I just get back my constraint. Okay? So then, if we look at these two equations, we see that lambda is proportional to the tension. And if you solve the Newton's equation way, you'll see that lambda is just negative of the tension. So one advantage that we have here by using the Lagrange multipliers is that we could solve for the tension. Right? So that's something that can be done. And one advantage of using the Lagrange method is that we actually don't have to work with things like that. We just have to work with the generalized coordinates and solve for theta. Basically, this constraint can be dealt both ways. Questions? right, so let me cover another topic then. When we talk about holonomic constraints, those are the ones that are written as an equation. Now let's talk so that we can talk about the non-holonomic constraints. And there's actually no general theory like Lagrange multipliers to solve when you have non-holonomic constraints. You can still solve the problems if there's a non-holonomic constraint, but there's no established theory to do it A, B, C, just like the Lagrange multipliers would have. What you have though is that some of those can be relatively easy to solve, but you have to take the approach, look at it and figure out how to solve it. Look at it and figure out how to solve it. There's no recipe to cover it. So for instance, what if you have inequalities? Let me give you an example. You have a particle moving under gravity. Here's a sphere, radius r. And then there's a particle P right here. And it is moving under gravity on the outside of the sphere. And outside the sphere of radius r. So then you have your constraint, and that is x squared plus y squared plus c squared. It has to be greater than or equal to r squared. R squared is the radius of the sphere, so that's your constraint. For this type of constraint, with an inequality, now you have a non-holonomic constraint. If it gets close to the sphere, we know that it's going to be at most in contact. And you could solve the problem when this is constrained to move on the sphere, right? On the surface of the sphere. So you have a particle on top of the sphere, and then you can calculate how it's going to move. If it was constrained to the sphere, you can figure that out. So that's a holonomic constraint. You can also calculate, you put it on top, and then you can figure out and calculate at what time is it going fast enough so that it drops off the sphere. So when it falls off, you have a different method to do it. It's not difficult, but you can do it, right? And you can figure at what angle is this particle going to stop being in contact. It started in contact, then it's moving in this direction, and then it's going to fall off the sphere. What angle was it with respect to the horizontal? So you can do that. It's not extremely complicated, but you can do it. So we have another example. And it's about velocity dependent constraints. So let's say that you had a constraint. Your constraint is going to be of the form x of a, x dot of a, t is equal to 0. So this type of constraint is non-holonomic. because you cannot make it like the if constraint that we have that didn't have this number here. So let me give you an example. A coin rolling down a slope.
So this is not orthogonal because of the XA dot phi.
Yep. So this makes it non-polynomial. Little velocity dependent part. So let's see. So I'm going to have a coin. The radius r. So this is going to have to be in 3 dimensions. So let's assume that we can draw in 3 dimensions. So this is the y direction. This is the x direction. Okay, so this is the xy plane. And this is like some wedge. And now on that wedge, we're going to have a point. There's a point now here of radius r. Okay. So x and y gives you the coordinate of the point. This is where it gets complicated. Let's say that we're looking at it from the top. This is x, this is y, and this is the point on the top. Okay. If you're going down the plane, right, which is the direction that the coin will go the fastest? Like this or like this? It's straight down, right? So actually, our coin has an extra degree of freedom because there's an angle right here, theta, right? So there's a theta, and this theta is the angle with respect to the steepest descent. All right, and then there's another constraint that we have for the coin, and that constraint is the one that is making an angle, let's say is touching here, and there's an angle phi. So this angle phi, right? If the coin was rolling, that's the angle with respect to the vertical, right? The angle of the coin. So if the coin is rolling without slipping, then when the angle theta, sorry, the angle phi is the angle that this point is making with this one, let's say, with the point of contact. So there's a point of contact right here, and then this R is located, is a point that we design on the like the initial point, and then we have how much it has moved in phi. So that's like its angular position of that point. And then we have that if the point is moving without, is rolling without slipping, we have that the velocity of the ring should be equal to the radius times the angular change. So if this is rolling without slipping, this is true. That's a constraint. If it's not rolling, if it's not, if it slips, right, then this is not true. Make sense? So now we have complicated things here. All of those guys cannot be integrated. So now we have basically, if we wanted to, there's this, right? So now, if we wanted to, we could have an equation that would look like this: x, y. Those are my two positions, x, y. Then I have theta, and then I have theta. Now, if I did all that, can I rewrite all of those constraints into a function that is equal to 0? And the answer to that is no, because this constraint right here already has that data value. So you see, this can be written. This cannot be written. Complicated, right? But there's no way to write it out as this is equal to 0. So that makes it non-polynomial.